Hi everyone. Thank you for coming this morning, and I'm very happy to be here. So I'm kind of from a sister discipline, so it's really nice to be able to be here and see what you guys are up to. And so today I'm going to talk about big visual data, something that I have been working on for a while. And you know, some of the things that I talk about is hopefully going to be kind of very familiar to you, and maybe some others will be a little bit kind of a different spin on. I've been working on kind of problems that are driven by visual data for most of my career, and so I can just kind of talk about some of the lessons that I learned and some of the things that I think are kind of promising, and also some of the things that one has to keep in the back of your mind when you're working with large amounts of visual data. I will start with visual texture, which is kind of a weird thing to start with, but I would like to say that it's really a microcosm of big data, right? Visual texture is basically, you know, just a single image of a phenomenon that somehow repeats. That's the definition of visual texture, that it repeats, right? And so in a way you can think of it as a one image encompassing a lot of different samples of the visual data, right? And one problem that I've been working on a while back that kind of started me on this big data story was texture synthesis. So given a patch of texture, you want to create more texture, but you don't want to do something like this, right? This looks very repeated. Human eye is very good at noticing this kind of repetition. You want to do something more like that. So how do you do that? And the classic, at that time, the classic texture synthesis methods were all kind of very much these kind of parametric models. You take a number of samples of texture, and then you try to kind of squeeze the texture in with a few parameters, and then once you have this model for the texture, then you can sample from that model and you can generate more of it, right? Kind of your standard approach. And the problem, of course, is this squeezing is very hard, because usually you don't have that many parameters, so you need to throw information away. You need to figure out what is it that you want to drop. And the problem there is that it's very hard to predict ahead of time what is it that you want to drop. What is it that's not going to be relevant to generate good textures? And as a result, the kind of standard approaches, they did not produce results that were very appealing visually, right? And I've been working in computer graphics, and computer graphics, it needs to be good. It needs to look good, right? And so what the approach that we proposed back then was basically forget the hard part. Just get rid of this bottleneck and just keep all the data around. Not try to squeeze anything into a parametric model. Keep everything around. And here is basically one slide summary of that algorithm. Let's say that you're synthesizing texture and you're doing it one pixel at a time. And here you already have synthesized a bunch of pixels, and now you're synthesizing pixel P. So what should be the color of pixel P? Well, in this non-parametric viewpoint, you have the original input image available, and so you make a kind of a Markovian assumption that the pixel P depends on the neighborhood of P, and you just search for similar patches in the input image, and then just pick one of those similar patches, take the central pixel of that, and transfer it over to P, and just repeat it over and over in kind of this growing approach, and slowly and surely you'll synthesize your texture. And this actually very simple algorithm ends up working much more convincingly than some of the kind of more complicated parametric approaches, even though it is really very simple. And so kind of the good news that I got out of this was that really stupid algorithms plus keeping around a lot of the data, in this case all of the data, gets you this unreasonable effectiveness. So there is this unreasonable effectiveness of mathematics paper a while back, and recently there has been a paper called The Unreasonable Effectiveness of Data that I worked on by some Google folks. And I encourage you to read that paper. It's a beautiful little 3-pager that kind of talks about this idea that when you have lots of data, you really don't need very complicated algorithms. Simple algorithms can do a lot of amazing things. And so this is the good news, and this is just in time because, of course, we are in a data deluge. The data is being spewed at us from all ends and corners, and the biggest big data is visual data, right? There is an amazing amount of data that we're getting. There is 72 hours uploaded to YouTube every minute. There is apparently estimated 3.5 billion photographs on Earth, and half of them have been taken in the last 12 months, right? So there's a huge amount of data. Cisco is saying that in a couple of years, 90% of the internet traffic will be visual data, images, videos, probably of cats mostly. But the thing is that this might be just too big, right? This amount of data might be too big for humans. There is a wonderful site I recommend to you guys. It's called Petit Tube. So it's kind of like YouTube, but what they do is you go there and they show you a random YouTube clip that has exactly 0 views, right? It has never been seen by a person before. Okay, and of course this is like destructive, right? Because once you see it, it's out of there. So go there and you will enjoy seeing, something that has never been seen by a person before, which kind of underlines, and there is tons of this, right? So this kind of underlines the fact that there is just a lot of what Pietro Pirone calls it the digital dark matter. There is a lot of visual data that has never been seen by a human, just sitting there, in the dark corners of the internet, and we don't have really a good ability to get to it, and because this kind of dark matter, this is exactly what people want to do with kind of data mining, data analytics, all this stuff, and you have this type of big data approaches in many other areas, and the one that's kind of conspicuously mostly missing right now is visual data, right? You don't hear about, startups doing, visual data analytics that much. There is a few, but it's not really there, even though it's this huge untapped resource. So why is this? Well, the main problem, and this is the bad news, is that visual data is just difficult. It's hard. It's as opposed to something like text, which is what most people do right now, right, on the web, is, text is clean, segmented, it's compact, it's one-dimensional, it's indexable. Visual data, on the other hand, it's noisy, and it's unsegmented, it's high entropy, it's more than 1D, 2D, 3D, maybe, even 4D with time. And so it's really a difficult problem. And really, the main thing when you want to do any sort of you go to any kind of data analytics or database class, and the first thing they say, okay, now you need to compare two pieces of data. The equal sign in C does not really exist for visual data, right? So a distance between two words, okay, you can do Hamming distance. A distance between 2 points in 2D, you can do Euclidean distance. A distance between 2 pixels, it's still okay, right? You can just do grayscale values. But what's the distance between those two things, right? Nobody knows, right? And so that, to me, is really the hard thing, that we really don't know how to compute visual distances in a way that allows us to apply all of the kind of classic methods. You can say, well, wait a minute, there is all these progress in visual search and retrieval. Surely we can do this, right? Whenever I go to the wine store, I go and I click, picture of a bottle, and then it tells me, how many points it got on Wine Spectator. The problem is that, that works really well when you have very, very similar or sometimes identical images, right? So, for example, here's a picture I took in Paris, Medici Fountain. I really like this place, and I thought, well, maybe I'm not so unique. Maybe other people took pictures of lovely place. And so I put it in, in Google image search, I drop in the image, and indeed, look at this. Not so original at all. So I decided I'm going to try harder, and I went in the winter. And Paris winters are not very, very cold, right? So you don't really have snow and ice that often. So I thought, oh, this is a pretty rare image. And I drop it in, and now we can see that it's not really getting, even though we know that it has a lot of the Medici fountain images, it is not really able to match them that well, right? So you see one, but then it goes kind of not so well. What about something like a painting, right? Well, it's not working so well at all. Or a sketch. I mean, sketch is really embarrassing. I mean, look at this. It's really kind of gave up completely, right? So the problem is really not solved for the type of visual similarities that we humans are accustomed to. And so I like to quote Jorge Luis Borges here from his short story Funes the Memorias. He said, this is about a fellow on an artistic spectrum, and it says, it irritated him that the dog of 3:14 in the afternoon seen in profile should be indicated by the same noun as the dog at 3:15 seen frontally. My memory, sir, is like a garbage heap. So basically, a lot of the visual data we have right now sitting on, in our image repositories and on the internet is like this dark garbage heap that we want to somehow organize and order, right? And so the first thing to do is to try to improve visual correspondence, right? To try to figure out if that particular point here, the yellow point, is our frontal dog. We want to find what are other dogs that that connect with it, right? And the simplest way to deal with this problem, of course, to improve visual correspondence, okay, one problem is you can be very clever and find a better distance metric. Another way to do this, much simpler in a way, just get more data, right? Because as you get more and more data, your distances become smaller and smaller, and then even if your distance metric isn't so great, it doesn't really have to have far to travel. It's already nearby, so even a bad metric will do okay for you. And so this is kind of we did this, a demonstration of this a few years back at SIGGRAPH, where, again, very, very simple idea. So, took a picture, and then I say, well, there is this a foreground that I don't like. I want to get rid of this houses in the foreground. Well, that's not a problem. I just go to Photoshop and get rid of it. But now I have a hole in the image. How do I fill in the hole, right? So kind of the same type of fill-in, but now we have this huge, huge hole. I can't really texture synthesize it. It's too big. And so the idea we had was just get a whole bunch of images. We downloaded 2 million images from Flickr. Back then it was a lot. And we just basically just did nearest neighbor. Let's look at all of them and see which one fits the best. And this was one of the ones that fit well, and we just pasted in little graph cut and Poisson blending, and it looks as good as new. And you can have fun things like you have a view from your house, and the hills look not so nice. Okay, we can get better hills for you, not a problem. There is some construction on your favorite beach. Never happened, right? So, why does this work? Basically, it's not the algorithm. Algorithm is basically nothing. It's just, look up, right? It's not that we are super clever. It's really about the data. So here is a demonstration. So when we started out this project, we thought, okay, we'll get a really big data set. And that 2007, we thought, okay, 100,000 images was a lot, or 20,000 images, I think, was a lot of data. Let's get 20,000 images. And let's find the most similar images in that data set, the nearest neighbors. And you can see that here for 20,000 images, these are the nearest neighbors for that image, and you can see that they're not very near. They're really not very good matches. But then my then student James Hayes, persevered and said, we still have some weeks before the deadline. Let me just keep downloading. And luckily we didn't get killed by Flickr for downloading all these images. And then exactly the same algorithm. We run exactly the same algorithm on 2 million images, and boom, it just started to work. So at some point, even something really, really silly, when you have enough data, the data starts to kind of speak to you a little bit. It's kind of starts whispering in your ear. Okay, so this is the unreasonable effectiveness right here. And if we step back and look at kind of the past successes, so what's the biggest or one of the biggest early successes of object recognition and computer vision is, of course, the face detection, right? Everybody probably knows Viola and Jones. Yeah, how many people know Viola Jones? Yeah, okay, yeah. So most people know Viola Jones. Actually, there were 3 papers in quick succession that all 3 got prizes in. They got the Test of Time award from, I think, a CUPR. There was Rowley, Baluja, Kanadi in 98, Schneiderman, Kanadi in 99, and Viola and Jones 2001, that all produced face detection results way, way better than before. And if you look at them, they used very, very different techniques. So, you have what are the things you have to pick? You have to pick your features, and you have to figure out what classifier you want to use for this, right? And so the first one used pixels as the features, and classifier was neural network, which back then was like, oh, very retro, it's not in fashion anymore. Then Scheimer and Kanadi used pairs of wavelet coefficients, and the classifier was naive Bayes, and then Viola Jones had the HAR, and the classifier was boosted cascade, which is why people are most familiar with it, because boosted cascade made it real time, and so you could have this super real time demos. But actually, Schneiderman and Kanadi was doing better in terms of precision, and I think actually probably the best phase detector out there. But the point I'm trying to make is that everything here was different except the one thing, and the one thing was the data. That is the time when people, first, they got access to more data, and second, they had this idea that actually we not only are going to use the positive data of faces in images, but we are also going to use the negative data, the patches in images that do not contain faces. That was kind of a new thing that came out, and really, all of these methods, while it's the features and the classifiers that people remember, really, at least in my opinion, it was really the data that made the breakthrough. And I think now, with a kind of a hindsight, I think that's kind of becoming more clear now. So, okay, now, this kind of a, very simple brute force scene understanding, what else can we do with it? Well, kind of the classic thing that people like to do is, if you have a way to find, given an image, to find a bunch of nearest neighbors, a bunch of similar images. Imagine that those similar images had some metadata connected with it, some annotation. Well, then you can transfer some of these labels from the data onto the query image and do some sort of visual understanding. And so kind of this simplest thing that, again, we did a while back was a project we called Im to GPS. You give us an image, we'll give you where it was taken, right? And the idea, again, was super, super simple. You take an image, you say, oh, where is it? I don't know. Well, let's index it into our large data set, and let's have the nearest neighbors vote on the GPS position on Earth to see what is the most likely spot. And here it actually correctly votes for Utah as being the place where this image is from. Okay, again, very, very simple algorithm, basically no algorithm at all, except we have the data, and the data, again, starts to whisper. We did a couple of works on doing this label transfer in the context of object detection. You got a classic object detector. Let's say you want to find buses and images. And it just basically finds your bounding box and says, okay, there's a bus, right? And so what we wanted to do something a little bit more. We wanted to find, can you find exact correspondence, kind of the most similar bus from your bus collection? And so instead of a single detector that just did the bus, non-bus, what we had is we had an ensemble of what we called exemplar detectors, where every bus was a classifier, and every bus says, how much does this thing look like me? And then they would all vote, and the winner would get it, and then you would basically say, okay, not only do I know that it's a bus, but I also can transfer a lot of the information particular to this bus, like, segmentation, maybe even a 3D model. And then you can see here, we show kind of showing off the correspondences. Now you say, not only can I say that this is that we have these detections here in the bounding boxes, but we can also in-paint the exemplar, the closest exemplar. And you can see the in-paintings on the right. They are very, very similar to the original image on the left. So kind of suggesting that we're really kind of capturing not just understanding the, okay, this is a car, but we are really saying, okay, this is this type of an SUV, which arguably kind of gives you more information about the visual data that you're looking at. And then you can do other things, like you can do prediction, for example. You can say, well, if you know that this is a bicycle, and let's say you have a metadata that says that you also have annotated people, and you can say, well, for this particular patch visual representation of the bicycle, it seems like there is in the training data there is a lot of the time you see this bounding box of the person on top of it. So then you can just transfer that bounding box and basically predict that there should be a person there, even though you don't have a person detector running, right? So you basically just from the bicycle you can just directly transfer the annotation for other things as well, kind of capturing context. Okay. So now that we can get a little bit of this distance working, we can do other things. Basically, a couple of examples of what can you do when you have lots of data and you have some semblance of a distance metric. And one example that we did a couple of years back at SIGGRAPH is something that I always was interested in, and this is kind of trying to understand visual data in terms of geography. People are really good at this. You guys are probably very good at this. So here is a question for you. One of these images is from Paris, France. This is actually just street view images that we cropped. Let's see if you can tell me which one. So clap if you think this is Paris. All right. Clap if you think this is Paris. Look at that, not bad. Okay, so for brownie points, where is the one on the left? London, yes, exactly. Very good. See, people are really good at this. And we are good at this despite the fact that this is some random street view images. There is no Big Ben on the left. There is no Eiffel Tower on the right. It's just there is something about the visual je ne sais quoi of these images that tell you the location. And we wanted to try to find this what is it, right? So we basically, the goal of this work was, given a large geotagged image data set, can we automatically discover visual elements that somehow characterize this visual location? Okay, what is it? What are the we can, of course we can just run a classifier and it will tell us if this is Paris or London. Actually, it does pretty well, but it doesn't tell us why, and we wanted to know why. Okay, and so our hypothesis is really what we want is we want to find visual elements that occur frequently in Paris and don't occur outside of Paris, right? So both of these things. So you can think really of it if you're familiar with text. This is kind of like TF-IDF for words, except that we also need to find the words. We don't have the features. And in language, you do term frequency inverse document frequency on word counts, but they have the words, so they can just count. Here we need to basically figure out what the words are. We need to find our features at the same time as we are doing TF-IDF. Okay? And so the idea is to capture, go to Google Street View, capture a whole bunch of images of Paris, okay? But also a bunch of other cities, just as your kind of negative set. And, Google Street View is great. We basically captured all, basically the whole city. And then what we want to do is we want to find these representative visual elements, right? And the first thing everybody does, of course, is to, okay, well, let's just cluster them, right? And hopefully things that look similar are going to be, close together in this whatever feature space we use, and things that are not are going to be far. So let's find tight clusters in this feature space. And of course, clustering k-means, sure, why not? The problem is that in high dimensionality, k-means doesn't work well, right? And we all know that, right? That when your dimensionality is in the thousands of dimensions, you get clusters that are something like this, right? That it's clustering on something. In its computer head, it definitely has some idea of there's something in common here, but it's not something that we care about, right? And so, it's not visually coherent. And so what we did instead is, again, a very, very simple kind of a nearest neighbor trick that seemed to work actually surprisingly well. So what we did was we first sampled a whole bunch of patches from all of Paris, okay? And I think maybe like 30,000 or something. And then we computed nearest neighbors for all of those patches, okay? And as we say, visual distance metrics are very hard, even though we used something reasonable. You can see that the nearest neighbors, most of the time, are not very good. You can see a few times it's doing okay, but most of the time it's not really, visually those nearest neighbors don't look good, okay? And so the first thing we did then is to say, okay, let's see what happens if we also look at the labels of these nearest neighbors, because we know which of the patches come from Paris and which patches come not from Paris, okay? And there is 50-50. There is 50% of the data is from Paris, 50% of the data is not from Paris. Can we just resort all of our 30,000 patches in terms of which ones have nearest neighbors that are mostly in Paris? And here is exactly the same data, just resorted by how many of its patches are indeed from Paris. And here you see two things happen. One thing that happens is, of course, now the nearest neighbors are all green, so they're all basically from Paris, which is what we sorted on, so we shouldn't be surprised by that. The second thing that is slightly more surprising that happens is that these nearest neighbors, these matches now, are all very visually coherent. They're actually very good matches, right? So why would this be? Well, it's basically, the idea is that if you had a set of bad matches, it would be very unlikely that you just by chance happen to get all of your nearest neighbors from Paris, right? It should be that you'll get basically, for incoherent matches, it should be basically 50-50, right? And so it would be very, very kind of it's possible, but it would be very improbable that they just all conspire to all be from Paris, right? If you see a bunch of things that are all from Paris, chances are it is because somehow the visual distance metric latched on to something that was Parisian in them. That's why they all worked out like this. And so this way, we're not actually trying to find the super duper uber distance metric. We're just kind of mining for the ones that are already just happen to be good by chance. And since we have a lot of them, then we hopefully can find a few that are like this. So that basically already gave us quite surprisingly good results. Unfortunately, one of the things that I really wanted to get is this idea of the Parisian street sign. They're very, very typical, these Parisian street sign. That doesn't happen anywhere else. And I thought, okay, we should be able, our algorithm should be able to figure out that this is very Parisian, right? And in our sorting, though, it was way, way down in the list. And so we looked at it, and we saw that for something like this, for example, the nearest neighbors weren't that great. So you can get you got a few of those street signs, but then a lot of them were just some random stuff. And then I was thinking, why is it doing this? What is it thinking, this computer? Why is it these are not nearest neighbors? And then I realized that actually these are perfectly fine nearest neighbors. It's just that computer didn't get the memo. It's doing something different from what we expect it to do, because we expect it to say, okay, find me the things that are the most closest things to this street sign. But actually, can you see what is it finding? It's actually very good nearest neighbors. But can you see what is it actually latching onto? Yeah, there is this thing. Look at this. It's perfect. The poor computer is doing exactly what you ask it to do. It's your own fault for not specifying your desires correctly, right? So the nearest neighbor is not a problem. It's a very high dimensional data. It's trying its best, right? So it needs just a little bit of a hint. And so what we did here, we say, well, look, again, we can use our labels and we can say, can we just make sure that the distance that it's computing is on something that we really care about? And we can say, okay, all we need is we need it to make the green stuff close, and the red stuff, well, we don't care really. It could be close, it could be far, but we want the green stuff to be close. And so now we are basically back in our kind of standard machine learning classifier land. We have a positive class and a negative class, and we want to push them apart, so it's kind of your classic linear classifier. So we can just apply something like linear SVM to the representation, and basically get, you can think of it as a weighting on our distance to say, okay, find me the weighting that would best keep all the green things close and all the red stuff far. And yeah, so after running a little SVM, linear SVM, we can get something that is better, so we can rerun the nearest neighbors and it gets better. Then we do it again, a couple of more iterations, and it just gets better and better and better. So it's basically kind of figuring out in this kind of weakly supervised way how to get the visual distance to be something that we care about. We are not telling it exactly what to do. The label is very, very weak. It's just basically one bit of information. Is it Paris or is it not Paris? But it seems to be actually enough to get us what we want. Okay? And so basically the summary of this approach is that we cluster, basically find nearest neighbors to every single patch, keep only the ones that are mostly Parisian, and then do this kind of iterative update to make these clusters better and better by kind of improving their little distance metrics. Okay? And so here are some images from Paris, and here are some of our clusters that we found that were basically the algorithm thought were very Parisian. Okay? So here is some of these clusters. It's okay, this is very Parisian. We also did it for Prague, London, Barcelona. America didn't work so well. So we thought, okay, the San Francisco, we should get something out of San Francisco, but basically we get some bay windows, it's true, but then it's basically like cars and driveways and things, right? Yeah. You could also, because we still have the GPS coordinates, we can actually kind of use it. So architects were kind of interested in this. They say, okay, we can find these visual elements, and then we can plot them on the map and see where they appear in the city. So here is a map of Paris, and you can see that these kind of grand Haussmannian balconies, they basically happen on the Grand Boulevard, right? Saint-Michel, Saint-Germain, whereas this little tiny little balconies, they happen in little side streets. So you can get a little bit of a feel about, you know, visual representation of a city. You could also ask a question, okay, if I have these visual elements that are particular to Paris, can I find something the most similar in other cities? And indeed, we can just kind of force these patches to be found in other images, in other cities, and we can actually use this to do a little bit of this visual data analytics. So, for example, here is kind of how the balconies change, right? So in Paris, they're all metal, and then in Prague and in London, they're more stone. This is my favorite. So turns out that there is this, in Paris, there is this ledge that sits right underneath a floor in some of the images, in some of the buildings. And turns out that in Prague, they also have a very similar kind of ledge, except it's between the floors, not right underneath. And in London, you know, they're all trying to save money, so there is no ledge there. So, but it's kind of nice. The other thing you can do is you can also compute, kind of look at the context given a particular visual element by just computing average images for just computing an average of all the images that have this this visual element, you know, aligned to the center, and then what we can see, again, we can do a little bit of analytics. We can say, oh, look at this. We can actually see that, you know, in France, it's all about, you know, equality and brotherhood, you know, égalité, fraternité. All the floors are basically the same height, right? Whereas in London, look at this. The first floor is very tall, and then it gets kind of smaller and smaller and smaller, right? So this kind of you know, national traits turns out to just come out from the visual data, maybe. We also applied it to other cases. For example, we say, you know, what makes X look like X? And so here is a data set. This is a MIT Indoor 67 of different categories, and you can see that, you know, this is kind of what makes a staircase look like a staircase. This is what makes an auditorium looks like an auditorium. My favorite, of course, is what makes a bathroom look like a bathroom over at the top corner. We also looked at yearbook data. We took pictures from yearbooks over the last 100 years in American high schools, and then we thought, okay, can we somehow capture, you know, what are the you know, the change of style over the decades? And these are some of the kind of discriminative types of faces. So this is the 60s and this is the 70s. So you can see that on the left you have the averages, on the right you have the kind of the faces that capture that are in that cluster, and you can see, you know, quite a bit of a difference between even the neighboring decades, how the styles have changed and what is the kind of the more classic look of the two decades. Okay, and that made us kind of think back to kind of the origin of these average images. So it's actually, the story starts with Sir Francis Galton, you know, at the very beginning of photography, really. He was the first one to have this idea of taking multiple exposures onto the same photographic plate to get what he called this composites. It's actually a Nature paper from like 1878. Really nice to read. What he wanted to do with them is less noble, I should say, but you know, it's definitely kind of a neat scientific trick that now we're calling image averaging, and it has been used lately in art, actually, in a big way. So there is an artist called Jason Sullivan that actually tries to use this medium of average images to give people a sense of what is the essence of a set of, you know, a set of images, basically, of a data collection. So here is this set is called the 100 Special Moments, where he takes us 100 images and he just averages them, and you can see that, you know, the newlyweds, I guess they basically all look the same. So it turns out that, the bride is always to the right of the groom. I didn't know that, but, this is, you look at the data and you see that, or that little leaguers are all basically looking the same, right? And we were very interested in this idea to somehow try to use the visual data to analyze and visualize what's in the data, since we can't just sit and watch Petit Tube all the time. So this is a paper we had last year at SIGGRAPH called Average Explorer, where we let the user try to use this medium of average imaging to explore what's in the data. And the reason we kind of started with this is that we just wanted to replicate Jason Sullivan's result, this kids with Santa, and we just went to Google image search and we typed kids with Santa, just what he did, and it didn't work very well. And then we kind of went back, and it turns out that actually he did a lot of manual aligning and cropping and picking different images to get it to work like this. And the reason basically is that there is a lot of data that doesn't really cluster well again, right? So there's a lot of different modes. You can have Santa could have a kid on the left lap, right lap, 2 kids, or maybe it's just some kid in a Santa suit, right? And they're all different modes. And so ideally you want to kind of compute different averages for every mode, and also of course they are misaligned, so you also want to align them. Right? So you want to do something like that. And so that's basically what we did. So the goal here was to basically have an interactive system that rapidly explores and aligns large image collections using image averaging. And so I'll just give you kind of a quick overview of the idea. Again, it's a very simple idea. Let's say you have all the images of kids with Santa, right? So first, let's compute the average. Well, that's pretty simple, right? This is your formula for computing an average. We can rewrite this in terms of weights on the constituent images. So we put these SIs there as weights on all the images, okay? Well, the idea of this approach is basically to allow the user to edit the average image in a way that controls the weights on the constituent images, that in turn recomputes the average and allows the user as kind of an iterative control where you edit the average and it gets better and better and better. That was basically the idea. And here we're just showing that it's just putting weights on the different images, but of course we also want to align it at the same time. So there is another thing going on in the background that tries to align the images to each other at the same time, okay? And so you get something like this. So basically that's the idea. And I can briefly show the tools, the tools that we use. So we had a bunch of different brushes that we allowed. One is a sketching brush. You basically just sketch whatever you want, and it finds it, and you can do it in gradient domain as well as in main. It's kind of related to the shadow draw paper a couple of years back. And it's, again, very simple to do, right? So you basically, as you sketch, you weigh the things that are corresponding in boundaries to your sketch as high, and everything else as low, and then you update your average this way, and things look good. The other is a coloring brush, where you say, I want to pick a color. Let's say I want to paint this black, okay? And guess what? It finds you basically people with sunglasses, right? So again, this very simple kind of a constraint, and you can combine the two. So for example, here we can use the sketching brush again to refine our Eiffel Tower, and then we can say, how does it look at night? Well, let's just paint the sky black and see how it looks at night. Look at that, right? A very kind of a simple interface. Now the main problem here is, how do you start? If initially when you're starting, the average might look really bad. Like it could be all washed out. Like this is the Stanta, average. It doesn't really, you don't know where, what to sketch. And so we had another tool proposed that we call the Explorer tool that basically allows you to move around the image and try to find little local modes, little discriminative visual elements actually from the previous example that allow you to kind of to see what's in the data. And so here, here we show what we did basically for every area in the image. We computed these visual elements, and then we clustered them into distributive groups, just like in the previous paper, and then we could then use that to only show the average with that particular mode, and then we can basically look at different averages from the same data, right? We also allowed the images to kind of self-align automatically, or to have a kind of when you click on something to get a little bit of an alignment where we automatically find where the similar things happens, and then hope align those images, and then the average becomes better. All right. So here is an example of this alignment. So this is kind of a whole bunch of images of the Bridge of Sighs in Oxford, and you can see that depending on where you click, it aligns at different places, and you can actually kind of do this exploration of the data set with the kind of changing the focus really of this data set. Okay. So we can now go back to the Kids with Santa and see if we can do better than before. And so here is our version of Kids with Santa with a user in the loop. And we can actually say, well, maybe there is more modes in this data, so we can create a new average, and then see if we can get the Santa, say, with 2 kids, and so we can use the tools to figure this out. Okay. Of course, what this should remind you of is clustering, right? This is really kind of a type of clustering with alignment. So how well does it do, compared to clustering? Well, so we ran a bunch of kind of standard algorithms, k-means, spectral clustering, discriminative clustering, and it does. So this is a data set called the wedding kiss. So lots of wedding kisses, it doesn't. These automatic methods, they try to do it, but they're definitely not as good as what we could get. So we could get something like this, this classic kiss, the close-up, the timid, British kiss, fancy schmancy one, kind of an artistic one. And this one, we were super happy. This is San Francisco, so turns out we got a gay kiss, which is quite cool, right? So and you can see that you can get nice correspondences too, right? So you actually, it's not only that you get a cluster, but you also get alignment of the images within the cluster. So the corresponding things within the cluster actually also get reasonably well aligned, which is kind of an added bonus. Of course, you can, now all of this was just so that we can do cats, the most important thing. So here is different breeds of cats. My student Junyan, who is the author on this paper, a really big fan of cats, and he wanted to see how do the different breeds look like, and this is what you'd get if you just average the images you scrape off the internet. But if you use our system, look at that, much nicer, right? Or if somebody here is from Amazon and wants to give us some money, we think this should be a great application for online shopping. You say, okay, I want this kind of shoe, but I want it in red. Can I do that? Sure, let me see. Look at this. Just paint red, and there you have it. These are the shoes you can buy. You say, well, maybe I need more stability on this shoe. Maybe it's too flimsy. Well, let me just paint it to be more stable. Look at this. Hop. And there you have it, and then you can, this is the one you want to get, and you just buy it, and we get 5%. Perfect. Right? So I go back to this thing and yeah, so this is all great and wonderful. So is data going to solve all your problem? Well, yes and no. Data is definitely necessary. If you don't have the data, you're screwed. But it's certainly not sufficient, right? So I think that there are two main problems. One is that we'll never have enough data, right? So this kind of a hole filling that I talked about, here you have a crane, you want to get rid of the crane, and look at this, perfect. Works very well. If you look at what's going under the hood, this is the first match. Look at this. It's basically the same. It's almost like an exact copy, right? Even though it's a different city, different river, but it kind of suggests that in this type of data, just because we humans are just boring architects and we always build the same things, and we humans are also very boring tourists because we take pictures of the same thing. These two boring things together kind of combine to get us something cool. But something like this is an image I took again in Paris, and it's once in a lifetime event. It will, this was a poster for a movie. It wasn't very good. It will never get played again. This will never happen again. No matter how long you wait, there will never find a nearest neighbor for this. And so you need to somehow kind of partition the image into manageable chunks that you can deal with. And I think here the big hope is the deep learning, which is a rebranding of neural networks from the 80s, but with lots of data, right? That's really what deep learning is. It's like you take neural networks and then you add lots of data to it. And so here we can hopefully be able to automatically discover these latent representative structures within the data that might not be the full image, but that basically find pieces that are repeatable and do this automatically. So that's kind of the big promise that I see in there. Of course, the downside is that at least currently, this is all supervised learning. So you need lots of labeled data, and lots of labeled data is very, very hard. We have infinite amount of unlabeled data. So really, what we want to do is unsupervised learning, but that currently doesn't work. But labeled data is also getting bigger and bigger, so there is hope. And the second issue is what I call data set bias, okay? And basically the problem here is that all of these methods, they work on some sort of data, and the data usually comes from the internet, and it's inherently biased, right? Internet has all these data sources, but they're not just random samples of the world. And here I'll just give you some examples. Again, you can see the Paris is a kind of a recurring theme here. This is, if you go to Flickr and you type Paris, this is the type of images that you're going to get. And this is also Paris. This is Google Street View Paris. Looks very, very different. And here is me just working on the street, right? This is also Paris. But that's basically the closest you can get to a real uniform random sampling of Paris, and it really doesn't look very Parisian, right? And these kind of biases are all over. So here is a classic example from psychology. Do you see some bias in this? Let's say you wanted to get mugs, data set of mugs from the internet. Do you see some bias in all of these mugs, or most of these mugs? Yeah, the handle is mostly on the right because we're right-handed, so we take a picture, right? That's not even something that you will notice right away, but it's clearly a very, very strong bias. Not even talking about the fact that there is plenty of times that you see a mug from above, from below, and it's very hard to find those on the internet, right? There is sampling bias. Where do people take pictures on? Well, usually on vacations. Notes how many pictures in Europe, and somehow not that many in Siberia. Somehow nobody really wants to take pictures in Siberia, right? For a photographer bias. You want to take picture of Paris, you want to, why do you do it? You do it so you can go back home to Nebraska and show it to your folks, right? So these are both pictures of the Notre Dame, and I think the left one, okay, I took it, but I think it's kind of nice and artistic, but it doesn't tell your folks that you've been to Notre Dame, right? Whereas the other one does. There is also social bias. We already talked about Jason Sullivan, the type of images that people take. And there is another type of social bias that this is Andy Gallagher's work that I really like. So he shows this picture and asks the question, So this is a picture of Mildred and Lisa. Which one is Mildred? Right? It's the one on the right. Why? Well, because there is data from the Social Security Administration on the popularity of names. And names correlate very much with age. So again, you have these biases that are there, but we are sometimes not even consciously exposed to them. So how much does this bias affect standard recognition algorithms? We did a paper with Antonio Tralba a few years back, and we basically said, okay, let's take a whole bunch of data sets and see, kind of standard computer vision data set, and see if people can guess which data set is which, just from a few images, okay? And ideally, all of these data sets are just samples from the visual world, so this should be a really, really hard task. But turns out, people are very good at this, at least computer vision scientists are really, really good at these tasks. And a very dumb linear classifier is also very, very good at this task, which is bad news, because that means that all these data sets are actually quite biased. And so, kind of to conclude this rambling presentation of mine, simple algorithms and lots of good data is actually kind of a magical thing that can get you very far in hard problems. And in fact, it's possible that we already have solutions to many hard problems. We just need to get enough data, or in case of deep learning, enough of label data to get there. But it basically it's all within reach. But we have to be aware and wary of this bias in the data, that whatever we want to solve, we need to make sure that the data we get is the data that ties to that particular problem, that is consistent with the problem at hand. Because otherwise you might get in embarrassing situations where you train on some data and it completely doesn't work for your problem. And so I'll close with this quote from a statistician: if you torture data long enough, it will confess. Thank you very much.
Okay, thank you very, very much. So I'd like to first off mention that after the questions, we will immediately go to the conference Best Paper Awards. So please do not leave following the questions. So thank you very much for a wonderful talk. We have time for some questions. There are 2 microphones that are set up in the center of each aisle. So I would like to invite people with questions to step up and see if we can be entertained and informed a little bit more.
Hi, Alyosha. Beautiful talk, as always. I noticed when you were doing the alignment in the averaging example, you get quite a lot of parallax information, and I was wondering if you'd thought about using that to reconstruct depths as well. When you do the alignment.
Right. So, I mean, for things like architecture, for example, this is in a way that's, you can just take like the bridge of size. You can just take that data and send it to, something like, the phototourism, Novus Navis work, and it will get you, structure for motion solution. I think, we did the bridge of size as kind of just a cool example for this data, but at least my feeling is that actually we want, this interface is more useful for things that are not really kind of geometrically related, that they're really more like, for things that are geometrically related, there are much better ways of exploring the data. Here we really want to, to kind of look at the manifold of Santa Clauses, which are, not something that you're probably going to get a 3D reconstruction of. Although actually there is some work that's beginning. For example, last year at CUPR there was a paper on reconstructing Pascal, where they take categories of objects and then they actually get a kind of a rough 3D models of them. So there is definitely something in there, but we haven't really thought about this that way. We're really kind of more of an interface to the human rather than rather to the algorithms. But yeah, maybe.
Okay. Thanks.
Okay, other questions? Bernice.
What a wonderful talk, thank you. I was wondering if you thought about applying this to something like understanding large medical databases. It occurred to me, large medical databases, let's say you have digital x-rays of, but people do have ideas of how they could be classified, but this kind of methodology, it seems that the structure in the data could speak for itself, and then with the interactivity of the medical doctor, maybe there are some kinds of structures that, of course you hope that the structures we know about would emerge, but maybe there are some structures that could emerge that would be even novel.
Right, no, we have thought about this, we don't have much expertise, so we haven't really done anything about it, but it is, yeah, it's an interesting question of, one way to think about this as well, really what we want is we don't need any doctors. We have x-rays and then we have, the diagnosis and we can just do this in a machine learning way and just go from one to the other. And then kind of the other viewpoint is that, well, the doctors maybe have some intuitions and some knowledge that somehow it's hard to code in just this input-output pair. So maybe how can we use the doctors? How can we just keep the doctors but help them? And in that sense, maybe just getting the doctors a way to align and kind of browse and
Exactly.
discover information on a large scale. For example, if the doctors were able to find hundreds or maybe thousands of similar cases for a particular X-ray, maybe they will see something that they wouldn't have seen if they didn't have this information, but also the automatic algorithm wouldn't have seen. So I don't know, but I think this is an interesting direction.